E-3DPSM, a state machine for event-based egocentric 3D human pose estimation. In this work, we present the first real-time state machine method tailored for egocentric event streams. While numerous methods have been proposed for RGB-based egocentric 3D pose estimation and have achieved high 3D pose accuracy, but robustness of these methods under conditions such as low light and fast motion remains a significant challenge, predominantly due to the inherent limitations of RGB cameras. Event cameras can address these failure cases and offer a strong alternative for egocentric pose estimation. Event cameras asynchronously record per pixel brightness changes in the scene instead of full image frames, unlike RGB cameras. This enables several unique properties such as high dynamic range, high temporal resolution in the millisecond range, and negligible motion blur. Apart from these sensing advantages, they also offer deployment benefits including low latency, low power consumption, and low data bandwidth. We now highlight the advantages of event cameras and pose estimation, focusing on two challenging scenarios, low light and fast motion. Here we see that event cameras offer high dynamic range, which is ideal for human pose estimation since human activities occur under diverse lighting conditions. They also produce negligible motion blur, which is important because human motion often involves fast movements. We now review existing event-based methods, EventEgo 3D and EventEgo 3D++, the first attempts at monocular egocentric 3D human pose estimation that recover human motion efficiently and achieve high 3D pose update rates in real time. But most modules of these methods have been strongly inspired by the RGB-based literature and adopted for the event-based setting. Hence, their limitations include the following. First, temporal modeling only through previous event frame. Second, it fails to fully exploit the properties of events as it predicts direct 3D poses at every step, ignoring the change-based nature of events and losing temporal continuity. Third, use of 2D heat maps can potentially lead to quantization errors. Fourth, the need for test time prediction of body segmentation masks serves as an additional source of error as supervision is required. Now we examine the results from these methods. Observe that there is significant jitter and noticeable inaccuracies in the predicted 3D pose, even for actions not leading to substantial occlusions in the egocentric views like walking. As a result, downstream tasks such as character animation are severely degraded. To address these limitations, we rethink this problem and present the key ideas that shape our approach. First, events capture changes in 2D. So we predict 3D delta changes that follow these event-level changes. This is one of our core insights in this work. Second, since events encode change continuously, we model 3D pose as a continuous process using internal states that evolve with the motion. We avoid intermediate 2D heat maps and do not rely on body segmentation, since we directly predict 3D pose, and the method is robust to background events. Key contributions of our work are: first, we introduce a real-time state machine method that maintains a continuous pose state aligned with event dynamics. Second, we present a new spatiotemporal encoder module that fuses spatial cues with long-range temporal dependencies using SSM. Third, we propose a learned pose fusion module that integrates 3D delta and direct poses to mitigate drift, and combines two sources of information into the final 3D human pose estimates. Next, we discuss our approach in detail. Our method takes monocular egocentric event streams and processes them to produce temporally consistent 3D poses. First, we convert raw event streams to 2D LNES representation. Next, our spatiotemporal pose encoder takes the LNES frame as input and produces temporally aware features. It uses res blocks and deformable attention for spatial reasoning and an SSM for temporal modeling. The SSM keeps an internal latent state that updates at each time step. Next, we discuss pose predictions at each time step. At the first time step, we predict the direct 3D pose and initialize both the SSM latent state Z and the pose fusion state X. From the second time step onward, the encoder uses the SSM's internal state to extract temporal features and updates this state based on the current input. We then combine these features with the embedding of the previous pose to predict the 3D delta pose, while a direct 3D pose is predicted separately. Finally, a learned pose fusion module uses its own pose state to fuse these predictions and update its state, giving us a drift-free and accurate 3D pose. Subsequent poses are predicted in the same way, following this continuous state machine. A simple way to convert the 3D delta pose to a full pose is to add it to the previous pose, but this causes errors to accumulate over time. To mitigate this, we introduce a learned pose fusion module that takes the current 3D delta and direct poses. It first performs a motion update by applying the delta pose to its internal pose state, then corrects the motion using the direct pose. The direct pose acts as an anchor for drift correction. We now show quantitative results. Our method significantly outperforms existing approaches on both E-3DPSM and E-3DPSM datasets. We also substantially improve the accuracy of occluded joints. This highlights the importance of our continuous state machine formulation. Next, we show qualitative results on the E-3DPSM dataset. We showcase crawl, kick, walk, and interaction actions. Here we showcase crawl and kick sequences, with crawl highlighting severe self-occlusions. Here for the crawl action, we can see that our method performs significantly better than prior methods, especially under these challenging self-occlusions. Next, we show results for walking and interaction sequences. Notice our method has significantly less jitter even under these fast motions. Next, we show qualitative results on the E-3DPSM in the wild dataset. We showcase various action sequences. Notice that there are significant background events in these in-the-wild sequences, making pose estimation more challenging even for simple actions. Our method performs better also in these scenarios, showing its robustness to background noise. Here we show more in-the-wild action sequences. Now, we will present a brief real-time demonstration of method on our portable setup. Here we demonstrate a scenario involving lower body occlusion and fast motion under low light conditions. Here we demonstrate walking and kicking actions in an indoor setting. Now, we will present our demo on a laptop with an NVIDIA 3050 Ti housed in a backpack. Here we demonstrate dance and boxing actions in an indoor setting. Thank you for watching. For more details, please see our paper.